Newton's method is very popular in solving the nth root problem. For example, computing square root of 2. The popular explanations about Newton's method relies on geometry. Start with the initial guess. You follow the tangent line. Then you will get closer and closer to the solution. But what does this algebra really mean? I don't know about you guys, but in my opinion, geometrical meaning is not the same as meaning. So in this video, I will discuss another way to understand this algorithm. It will help you understand why it makes sense in the first place. We need to step back and think about the nature of numerical method. If we compare square root of 2 versus 2, here is the difference. 2 is a number, you know what it is. Square root of 2 is not a number yet, because you don't know what it is yet. It's a condition for this number to satisfy. That is, square of it will give you 2. So when we use numerical method to solve it, we transform this condition into a puzzle, saying which number when squared gives you 2. And numerical method is guess and see if it works. To solve this puzzle, the simplest way is to start with a guess. For example, we know the answer should be greater than 1, so we start from there. We check if squaring it gives us 2. If not, we make the next step at certain intervals apart. If not, try the next one, and so on. This method is the simplest version of numerical method. It's simple, but it's very inefficient because it uses a static step size. Your step size really matters here. If it's too big, you might miss your solution, but if it's too small, it might take forever. But the difference between your guess and the target has meanings. The greater they are, the further away you're from the right answer. So that means when you're far away from the answer, you should make a bigger stride. But when you're closer to the answer, you should make a small step. Our naive search method does not use this information. That's why it's very inefficient. But Newton's method takes that into account. Let's see how it does that. Say x is our guess. It won't be right, so we need to adjust it by delta x. Now, how to adjust it so that we can hit the right answer quickly? Well, we should adjust it based on how far it is from the right answer. Its square difference from the target 2 is the arrow, giving us an idea about how far we are from the target. Now we want to know how much we should adjust the guess by. We don't know yet, but we know how much we want this arrow to change by. We want it to go to 0. Hence, we want the arrow change to be the opposite of the current arrow. How can this tell us how to adjust our guess then? Because there is a relationship between the guess and the arrow. So that means when your guess changes, so will the arrow. Hence, there is a relationship between the change in the guess and the change in the arrow. So I should adjust the guess based on this relationship. Say if our guess changes by this much. If the arrow changes by the same amount, that means I should change my guess by the same target arrow change. But if the arrow changes twice the guess change, then I should adjust my guess by half of that. If the arrow change triples that of the guess change, then I should update my guess by a third of that. In other words, our step size depends on how fast the arrow changes with the guess. And that speed is the derivative of the arrow function, telling us how fast the arrow changes with our guess. If we plug that in, we have step size equals to the negative ratio of the arrow and the speed of the arrow change. So here's the algorithm. You start with the initial guess, compute how far you are from the target, divide over how fast the arrow changes with the guess. Use that to update your next guess. Then calculate the error and the speed divided 2. Use that to update your next guess. Then calculate the error and the speed divided 2. And so on. In general, you update your guess based on the speed-adjusted error. Now let's see how it connects to geometry. At each guess, we calculate the error. We can put a point according to the guess and the arrow along the vertical direction. So we have a curve representing the relationship between the arrow and the guess. Now, at any guess, we can use this formula to calculate the arrow. This is the height here. The speed at this point is the tangent ratio of the tangent line. So if you divide the height over the tangent, what do you get? You get these horizontal length. This is our step size. Therefore, it means the effect of this ratio is equivalent to traveling along the tangent line to get the next guess. Then go up again, follow the tangent line, get the next guess, and so on. What I want to emphasize is I see so many people using geometry to explain math. True, they are better than no explanations. But remember, geometrical meaning is different from meaning. We shouldn't be content with geometrical meaning only.